everybody, what is happening today? Another week of CS302, week 2, day 1. Hope you all had a great weekend. Today we start the real CS302, and I look forward to that. Hello, hello. So, today we are going to be looking at asymptotic complexity, and if we have some time at the end, we will start talking about recurrence relations. And like I said, this is a hard topic, the recurrence relation part at least. But before we kind of give you those definitions, let's kind of backtrack a little bit and talk about what a data structure is, since that is the name of the course. So it's good to define that name, right? And so to do that, we first need to define what an abstract data type is for that. And as you can see, I did bring out my notes out for some of this stuff, so because I will be referring to my notes. So an abstract data type is basically a set of values and operations, and you probably learned that when you were taking 202. Well, that looks kind of pixelated, but interesting. Okay, so that is an abstract data type, and it's basically a set of values and operations. And so a data structure is basically an implementation of an abstract data type. Implementation of an ADT. Not like the security company, okay? And so the typical things that a data structure will do, which I did kind of bring up last time or on day 1, is you basically want to insert data into your data structure. You typically want to be able to retrieve that data at a later time. And optionally, there's some sort of in-between stage there to process that data. How you process that data is up to you. You might be sorting the data. You might simply be processing it to store it in a special way to speed up retrieval. You may also be storing the data in a way to save space. So you might be messing with the data. So there's usually some sort of processing stage in the middle, right? But primarily you want to be able to store the data and then retrieve the data. And I suppose it goes without saying, when you're done with the data after you retrieve it, you may or may not want to actually delete the data, right? So let's go ahead and write those down just so we remember. So you want to be able to insert, retrieve, delete potentially, because we don't want to be able to retrieve the data without deleting it. But sometimes, typically, people put retrieve and delete at the same thing, because usually when you take data out, you also want to remove it. But it might be optional. You might actually want to keep it and just retrieve a copy of the data, right? And then modify the data, I suppose, as well, which we also talk about it as process the data. Okay? So anyways, that's hopefully all of review from before, okay? What I'm going to talk about more is a little bit about this whole concept of, you know, what kind of things you can do in that modify or process stage and why you do them, right? You want to usually have, it always comes down to these two words. You want to make something faster, or you want to make it take less space, okay? That's what it ends boiling down to. And so that brings up to these two very important words in this class, which are space and time. And in general, I mean, in life, space and time are like the biggest things, I suppose, right? And so space and time. Let's talk about how these things are implemented in the computer. When I'm talking about space in the computer, what am I typically referring to? That's a question for you guys. So chat. When we say we're saving a lot of space, or I just bought this machine and it has a lot of space for store stuff, what are we talking about? Amount of main memory used. That is correct. So we are talking about memory in terms of bytes, or a bigger measurement like gigabytes or terabytes of memory, right? And those kinds of memory are split into two categories. And if you took 219 already, then you know, and if not, then that's okay, I'm about to tell you, right? So one of them, as you guys said, is main memory, which is typically the RAM, right? So you got main memory. And what's the other one? Where's the other place where you store things? Like, where would you store Warzone with its, what, 200 gigabyte thing? Secondary storage, that's right. Secondary storage. What are some examples of secondary storage? The two most popular ones. Hard drive and SSD, that is correct. So hard drive disk and solid state drives, right? The difference being that solid states are faster, but they're more expensive, and the reason is because it's newer technology. Hard drives are just literally disks that are spinning in there, and you learn more about this in 2019, so I'm not going to go too deep into it. But that is, you guys are correct. When we're talking about space, we are referring yes, we can talk about it theoretically, but in practice, we are referring to the amount of data in terms of bytes that a program takes to run. And that is how much it needs in main memory typically to run. And then to store that program or the data that the program is dealing with, you may need to store that in the secondary storage. Now, ideally, we would like to always have everything in main memory, because main memory is way, way, way faster. We're talking by factors of thousands of times faster than secondary storage. That just happens to be with the way the technology is for something like a hard drive or a solid state drive. But even within a hard drive and a solid state is way faster than a hard drive. And so ultimately, space is expensive. Main memory is expensive. A couple of years ago, there was that shortage of RAM, and RAM prices went up a lot. I frankly don't know if they've come back down fully, but memory can be expensive. And so sometimes, a program or a specific algorithm takes a lot of memory to run, and we may not have that memory. So sometimes, we need to make sacrifices and say, okay, we can't afford 500 gigabytes of RAM to be able to run our bubble sort. So we are going to have to either improve our algorithm, or we are going to have to slow things down to use secondary storage to store part of the data set. Okay? And in practice, an example that I can give you is that I was working on actually downloading Wikipedia and generating the dictionary of Wikipedia, amongst other things. And to do that, I had to look at the entire Wikipedia website, all of the articles there, basically read through them, not me, but the computer, find all of the words, and then create a dictionary along with the frequency. To do that, I need to download Wikipedia and process it. Ideally, it would be great if I could just literally load Wikipedia into RAM, look at it once, and then be done with it. But of course, Wikipedia is relatively big, but it's not as big as you would think. So I was actually able to load it into a special computer that we had there that has 500 gigabytes of RAM, and I was able to load all the text. The text is, I believe, like less than 100 gigabytes of text. It's actually much less than that. So it's definitely doable. So yes, it has no redeeming features whatsoever. Bubble sort can be useful because, like, for example, you can code. Oh, okay. We'll come back to that when we talk about sorting, but bubble sort is both stable and an in-place sorting algorithm. Two things that are very nice that quicksort does not have for stability. So there's one pro, although there's merge sort. But don't just totally throw away bubble sort. That's from the textbook. Oh, well, there you go. But still, I would say bubble sort does have some redeeming qualities to it. So anyways, that's one side of the coin, space. The other side of the coin is time. Now, time is a lot easier to explain to someone because we all understand the concept of time, right? Oh, a second just went by. We're never going to get that second back where I said nothing, right? That's kind of the concept of time right there. And so when we are talking about time in terms of a computer, it's a little bit more, shall we say, complicated to talk about that. But you can still talk about it in terms of seconds or like actual physical time. But sometimes it's useful to talk about it in terms of clock cycles or operations per second. I guess if I make it a little bit bigger, I'll be able to write better. So, operations per second. Okay? So these are all different ways of measuring time in a computer. One way is whose bubble sort is faster, yours or mine? Okay, how about you run yours in your computer, I run mine in my computer, and then we time them on the same data. and mine ends up finishing like in twice the time that yours takes. And you're like, ha, mine is faster. But it turns out that my computer is really bad and your computer is really good. And so there's a lot of external factors that are going to modify or change how long a program takes beyond just the program itself. Because of that, physical time is not ideal unless you have the exact same systems, right? If your system is the exact same as mine, and everything else is the same, then sure, you could use time for that. But that's very rarely the case. We all have different. Oh, by the way, I didn't bring the microphone closer, so let me bring it closer. So that really can play with our results. So like when we're really trying to say like, oh, we just came with the state-of-the-art algorithm to do sorting, the best sorting algorithm ever, you can't just be like, I ran it on my computer, it ran faster than your algorithm that you run in your computer, because different architectures, there's a lot of different factors, right? So seconds, while useful, if you're running it in the same computer for good comparison, and then you're averaging out a couple of runs, can be good. It's not ideal. On the other hand, we have ways of measuring internal operations like clock cycle, where each clock cycle you can do a single operation on the CPU. That can be useful to kind of alleviate some of the different computers running, but it's a little bit too low level for our taste. So a good middle ground is basically operations per second. Okay, and operations per second can be something that we can define on the algorithm. I'm going to keep going back to sorting, because that's the one that you know so far from like 135, even though you don't know a lot, but you know at least what sorting is, right? So I'm going to keep going back to sorting when I'm talking about these things. When you're thinking about sorting, what do you think would be an operation in sorting that we could measure? Like to see which algorithm is better, yours or mine, which bubble sort is better. What do you think that operation would be to measure? Number of comparisons. That's a really good one. Wouldn't clock cycle also be influenced by system hardware? Clock cycle can be faster or slower, but the number of ticks would remain consistent if your hardware can do certain operations per tick, which is why, yes, you're right, there's some variations, so that's why it's a little bit iffy, but at the same time, it's much better than second. So comparisons or swaps, that's very, very good, both of those. So operations per second can be defined in sorting as the number of swaps you do if you need to swap things around, but also the number of comparisons, which is more important, because if you're sorting something, the act of you looking at two numbers in bubble sort and making sure that they're in the right order, that means you have to look at one number, you have to look at the other number, you have to compare the numbers. That is an operation that takes time. To load that data potentially from the hard drive or from main memory into the CPU takes time, looking at the numbers, doing the mathematical comparison, bit by bit or whatever, character by character, and then making the decision to swap them or not. Swapping also takes time, but more importantly, we typically look at the number of comparisons, because even the list is completely sorted. Let's say the list is sorted, but our algorithm is just so bad that like, even though the list is sorted, it's still gonna run and check every single number multiple times. And I'm gonna show you a way of doing bubble sort like that, and I'm gonna do a way of avoiding that. So if we do that, we could have an algorithm that is like, oh, it has 0 swaps because the list is sorted, so it's really good. Yeah, but you have to do like a billion comparisons to actually make that decision and say, oh, the list is sorted, no swaps needed. So comparisons is a very useful thing. And then in other algorithms, there's going to be other operations that are typically something like a comparison, but it depends on the algorithm, as a way of measuring how efficient your algorithm is in terms of time. Okay? So going back, we have again space and time. Both are very valuable resources. Back in the day, I would say that they were both as valuable and both as scarce. Nowadays, things have taken a little bit of a shift in computer science to more of space being more readily available and cheaper, and time being the more valuable resource. Nowadays, yes, we have big data. Data is growing at a faster rate than our technology is being able to handle it. So like, we have bigger and bigger hard drives every day, bigger and bigger RAM and everything, but the rate at the side of, like, think about RAM, how quickly RAM is sort of going up in size, right? What is the average right now? 16 gigs of RAM is like your average computer, maybe 8 gigs of RAM, it's like lower end. I don't know, maybe I'm out of touch with that. My computer has 2 sticks of 16 gigs of RAM, which I bought 4 years ago, but they're pretty expensive, I think, at the time. So I don't know. But I think that the norm is definitely not 32 gigs of RAM. So 8 to 16 is average. Okay, that's good. Yeah, so that's what I thought as well. So that's been the case for like the last 5 years. And before that, the average was 4 to 8, and then 2 to 4. But like the amount of time that we went from like the average being 4 to 8 to making it 8 to 16 is a lot slower than the amount of data that we're generating as a society. Like internet, Google, Facebook, you know, there's so much data being generated every day in the order of, I think Facebook processes, or Google, I can't remember which one, processes, I think 6 petabytes per day of data, or per hour. I don't know. Maybe it's per day. But that's the amount of data it processes because it gets generated every day. That's people writing posts and having to read that and sort it and do some data mining to sell you stuff. That's a lot of data. And that keeps growing. If we look at the chart of how things are growing, you know, it's going like this. It's exponential. Our RAM is more of like squared, like parabola style, I suppose. It is growing a lot slower. It's not keeping up. However, it is still going up pretty big for smaller projects, right? Because like back, you know, if you're doing something that doesn't require big data, we still have a lot of space nowadays compared to what we did back in the day. And because of that reason, even though data is just growing insanely in the world, data for like other than big data has kind of remained around the same size, whereas we are still growing in terms of RAM and hard drive space. So space has become a lot cheaper. Time, unless we figure out a way of having eternal life, is still very valuable and limited. You know, our age span has not increased that much over the past couple of centuries. And so we're still limited to like, what, 100 years pretty much being the thing. And so that doesn't mean we want a program to run 100 years, right? We want a program to run like, hopefully immediately. So that is going to be the most valuable resource that we have. And so what ends up happening with algorithms is a lot of times we'll try to go and make an algorithm fast in terms of time without much concern for space. And that is typically the norm, with the exception of like when you go hardcore and crazy. Like when we talk about direct access methods and hashing, which is one way of achieving really fast access time, that is, I think, the only case that we'll talk in the semester where we'll be like, okay, yeah, space is like cheap and we have a lot of it, but like this is where we draw the line. Like this is okay. This is too far. Okay. But other than that, I think for the most of the semester, we're really focusing on the time aspect versus space. Okay. But we will still, you know, try and visit the space of each algorithm we look at, because what we're going to do is all the algorithms that I show you in this class, we are going to analyze the space and time of each of them. Space and time complexity is the name. But really, the honest truth, even though I say we're going to look at both, is we really focus on the time component. We don't really look much at the space. Like we kind of just talk about it really fast and then just kind of forget about it because we're like, oh yeah, this takes this amount of space, but whatever, we got a lot of space, so no worries. Worry more about making it fast. That's what it turns out. Like that's the reality of things these days. And so just be aware that there's always a space component. And like I said, it's only really going to come into play when we talk about hashing. I can't remember any other algorithm this semester where space really comes into like a problem. And by that I mean like, you know, where yes, we can gain speed at the cost of like insanely increasing the amount of space required for something to run. And like I said, I can't think of any other example other than direct access mapping, which is something that we talk about with hashing. So I did a hash lecture in VR on YouTube if you're interested in that. I'm skipping ahead. But okay, so that's space and time. And so what we want to do is be able to look at an algorithm, analyze it, and decide how much space and how much time it takes. Okay, so next, let's go ahead and talk about algorithm analysis. And I think it's with, you spell analysis with S, but I'm not sure. It might be Z. So what we need to do is figure out when we're looking at a problem, how we're going to solve it, okay? And so typically the process for that is first you want to identify what you're trying to do. Identify the problem. And what does that really mean? Because that's like saying, you know, step one, do this. Step two, you're done. No, you got to break it down further. What you need to do is you need to identify the different aspects of what you're trying to do. It might not even be necessarily a problem. It's more of like a goal that you're trying to do. So what you want to do is you want to identify a couple of things. You want to identify the data that you're working with. You want to identify what operations on that data you need to do. And then as you do those things, you are going to come into sort of this space and time analysis and identify, more importantly, the resource constraints. The resource constraints are going to be things like how much RAM we have. Can we run our program? Do we have enough space to store the data for it? How much time do we need? Is this an application that needs to be running on real time? Like it needs to be running like let's say it's we're making a social distance detector and it needs to be running like live feed. You know, it gets the video camera footage and needs to be running what is known as real time. Okay, so I'll write that down because I actually couldn't remember that for a second there. So I'll write it in for myself too. So real time. If you need to run something on real time, that puts a lot of constraint in your systems because you can't have a delay, right? Otherwise, you need to have an expectation about how long do you have to complete the task, okay? So that's the time aspect. And then the space aspect for the resource constraints, like how much space do we need, okay? So now that we need to figure out a way of analyzing a problem or a math problem or whatever we're trying to do and put it into measurable terms that then we can compare and say, okay, you know, we're looking at bubble sort here, and we need to figure out how much space is bubble sort going to take to run in our system and how much time it's going to take. One way to do it is we can just YOLO it and just try to load it in the computer. If it loads, it means that we have enough space, and then we just run it and then we time it. And then when we run it a few times, we can kind of take the average of those times and be like, well, I think this is how long the algorithm takes with this size of data. And then somebody asks, well, what if you feed it twice the data? You're like, maybe multiply times 2, I guess. I don't know. Or you multiply, or is it squared? Like question mark, right? So what we need to do as computer scientists, because that's what we all are striving to be, is unless you're CPE, in which case, blah. But what we're trying to do is we're trying to find a way of intelligently expressing how long a program takes to run in terms of what is known as asymptotic complexity, which is where big O notation is going to come into play, okay? Which is the goal of the lecture, okay? So this was all kind of hyping you up and building up to that, okay? So we want to be able to communicate to others how long a program takes in a nice and easy way to express that has nothing to do with seconds or other sort of things that are not very accurate or they matter on our architecture. You know, we want something that is very easy to communicate and say like, this is how long it takes, and they understand it, like they get it. They don't need to run anything. They don't need to ask what hardware it is. That you just get it, okay? And that is basically what big O is. So again, this is asymptotic complexity. Why is it not letting me write? It's not letting me, right? Hold on a second, guys. Technical problems, like it's just not doing something. Let me try backing up and going back in. It's like highlighted. I write, but it just shakes. So let me restart the program. Give me 1 second, guys. There we go. I think it's good. Let me try. Yep, it's good. Okay. Let me pull up my notes as well. Not this one's. here we go. Nope, not these ones as well. Sorry, I had to close my notes, and now I'm looking for my notes because I have the formal definition of big O in those. So just give me 1 second. Oh gosh, now it totally crashed again. All right, stand by. Give me 1 second to get this fixed. Okay, let's try this again. So let's see. Okay, here we go. So this is that one. So now I just need to load this over here. There we go. Okay. All right, we're coming back now. Okay. We're good now. So, I mean, like, normally I can do this off memory, but this is that one topic that, like, I have these pictures drawn and I want to pull it up from the other notes that I did over the last semester, because that saves me having to write a lot of math symbols. And so, yes. Okay. So before anything bad happens, let me go ahead and actually copy and paste what I wanted to copy and paste from my other notes. Okay. And let's just do that now before something bad happens to this. Copy and paste. Okay. All right. Cool. Okay, so big O. All right. So there are three sort of different bounds that we're going to look at when we're measuring an algorithm. Okay. We are going, and then an easy way to describe them, albeit a little bit misleading, is to say we want to look at the worst case scenario, we want to look at the best case scenario, and then, and this one's the one that's misleading to say, we want to look at what will be the average case scenario. Okay? But that's very misleading to say the word average. Okay? So it's, you know, it's useful to know. If I tell you, like, my algorithm on average takes this amount of time, and again, I'm still using the word time. I'm going to show you a better way of using things in a second, but before I show you that, I want to use that term and then confuse you, okay? So I can say, my algorithm on average takes 5 seconds, okay? And that is useful to know because then I can compare it to other algorithms who might on average take 6 seconds. And I can confidently say, my algorithm is faster in most cases. However, here's the thing. There's something with my code, and in the edge cases, my algorithm actually takes 2 hours. Like if you get this really weird case. However, their algorithm, even though it's slower on average, in the worst case scenario, it takes 10 seconds. So you have a situation where your algorithm is on average per se faster, but there are some cases where it's really bad. 2 hours is really bad. And so suppose that what you're doing is not that time critical and you can afford to have that occasional 2 hour period for those really weird cases. That's okay. You might still think your algorithm is better because on average it'll be better. But suppose this is something life or death and you need it to be like real time. And then there's a case where like it's no longer real time because it takes 2 hours. Then it's bad because now you're like, okay, you can't just like freeze the breathing system for somebody for 2 hours, you know? So essentially, that is something very important to always know, is what is known as the upper bound, which is the worst case scenario. That is going to be what big O is. And I'll go over the math in a second. On the other hand, it is useful, albeit not as useful, but kind of nice to know, the lower bound. What's the lower bound of an algorithm? The lower bound of an algorithm is going to be kind of like the best case scenario. That is going to be the scenario where your algorithm can never ever be faster than this. even if you give it the ideal data. Okay? As an example, think about sorting again. What do you think would be the ideal data to be given to an algorithm? And I haven't said which algorithm, but let's just say bubble sort. What do you think would be the ideal data set to be given to bubble sort to make it finish in the least amount of time possible? That's a question for you, Chad. What do you think? $39 viewers. A set already sorted. Oh, you are correct. That would be typically what would be known as the ideal case. If it's already sorted, more than likely all it's going to take is you looking at the list once and being like, oh, it's already sorted. I'm done. GG easy, I guess. Right? Yes and no. 99% of the time, you are right. However, some algorithms are not that good. And so even something I think like quicksort would not really benefit from getting a sorted list, I think. They would still not be as fast as just looking at the list once and calling it a day. As strange as that sounds. Bubble sort, yes, you can do that. But only if you do a little change in the code. Bubble sort, typically, you're running two loops. One inside of the other one. And you need to put an extra Boolean value to check if you did any swaps in that iteration. And if you did, then keep going. If you didn't do, that's the sign that you're done. But if you don't add that little piece of code checking that there's no swaps, then your code is still going to do the amount of comparisons that it would normally do, even if the list was not sorted. So it's not an automatically given that the list that a sorted list is going to automatically make the best case. Your algorithm might just be so bad that there is not even a best case. They're all bad cases per se. Okay, but anyways, lower bound, that's what it is. And again, we'll talk more in detail about sorting, but again, I'm just using it because that's the one that most people know at this point. Lower bound can be good and known as the best case scenario for the most part. Okay, finally we have, and that's called big omega. Okay, like omega low, omega. All right, so finally we have theta. And again, this is a very risky one to say average because it's not really average. It's more of what I put in here as something in between. But I want you to just kind of interpret that as kind of like the most common case, the mode per se of the algorithm. That's the one that typically you care about because you kind of want to know, like, okay, yeah, sure, worst case scenario, best case scenario, but what is the real, like let's be straight, what is going to be, how long is this going to take to run? That's kind of what your big data would be. Okay, and so how do we actually define this? Well, to understand this math, we need to kind of look ahead into what asymptotic complexity is of code. So I think we start with that and then we come back with this, because last time around I went straight to the math and people were lost and scared. The best and worst average cases have their own upper and lower bound. It's a good question. The answer is not really, because the best case by definition is the best case of the entire algorithm. There's no best worst and best best. There's a best case. Yes, I agree with you in saying of the edge cases, this one's like the best of the best and this is the worst of the edges. Yes, but not as an overall analysis of an algorithm. Okay? Can we say that every algorithm has an upper and lower bound? Yes. They don't necessarily have to be different, but we can confidently say that any algorithm has an upper bound and lower bound. That upper bound and lower bound could be infinity, by the way, but that's still a number. Well, that's risky to say, but it's still a measurement per se. Okay? Can a lower bound be equal to the upper bound? Yes, it can. Bubble sort, written the really bad way, is the best example of that. And by bad way, I mean the simplest way, where you just put the two loops and you just like swap things around. That would be an example of a lower bound and upper bound being essentially the same. Optimal algorithm with upper bound of 2. I left null. An optimal, well, I know you're making a joke, but you screwed that up. But anyways, yes. But yes, you can have that. And we will see examples of that. But yes, these are all good questions, so keep them coming. I like them. Okay. So before we revisit, we look at the math, because I don't want to scare you with this. Let me show you something a little bit more of what you're familiar with, which is code, okay? So let me talk to you about asymptotic complexity and the notation, okay? So let's look at the big O, okay? So big O, typically you will see something in this format, something like O of n, okay? And you might be asking yourself, what does this mean? I'm glad you asked. What this means is an asymptotic complexity and an upper bound of n time. What does n time mean? N means linear time. And let me show you the pattern here. Let's say you see something of the n squared. What does that mean? That means quadratic time. And by the way, the entire thing I'm about to talk about applies also for space. So like linear space, quadratic space. But we're going to focus on time for now, okay? Can some algorithms are more, that's not grammatically correct. I think you're missing a word. Can some algorithms are more than one, I think you mean have. Can some algorithms have more than one upper bound and lower bound? Or should we consider our algorithms to have at least an upper bound and the greatest lower bound? So algorithms should only have one upper and one lower bound overall. However, there's sort of, see, it gets tricky, but I would say for now, just think of it that way. You can only have one upper bound and one lower bound, okay? And one theta as well, I would say. Yeah. It's a gray area for some cases because like big O notation, like for example, there's something known as the lower bound for comparison-based sorting. And what that means is the best case scenario for any algorithm cannot be faster than this time. And that sort of sounds weird because I'm using the word best case when talking about lower bound. But it's more like the best worst case, really. Yeah, the best worst case. Yeah. So for the lower bound for comparison-based sorting, and I will bring this up when we talk about sorting, is actually what is known as O n log n. Okay? That's the lower bound of comparison-based sorting. What that means is that no matter how smart you are, you cannot come up with an algorithm that is better than that. Which means that even though n log n is referring to the big O, which is upper bound, we are still talking about it in terms of best. The reason for that is because what that means is that we can't make something faster than that. So that's why using the word best and worst is kind of iffy for using this. It's a good introduction, but eventually we want to transcend from these terms. So we have to be careful. And then with the upper bound and lower bound, you know, you can still talk about something in terms of big O when we're talking about the lower bound of it, which is what this case would be with the comparison-based sorting. So for now, I'm gonna just stick with that. There's only one for up and one for down, but sort of keep back in your mind that we are gonna revisit that sort of definition as we learn more about this. Okay? So yes, every rule is meant to be broken, kind of thing. Okay? So yes, gray area for sure. All right. So linear time, quadratic time. What does this mean? Let me go ahead and start by giving you a piece of code. Okay? Let's write a little for loop. And this is kind of what your next assignment is going to be like. It's not you're not coding in your next assignment. I mean, not really coding. You might have to write some code, but it's more of a paper assignment per se. So let's say you have a code like this, and then you have just some code in here that's irrelevant to us, okay? And maybe we make this into a function. So let's call this foo. Curly brackets are a real challenge for me. There we go. Okay, so we have a little function foo. This little function foo has a loop in it, and this loop runs from I equals to 0 to I is less than n being the parameter passed into the function, okay? And then there's some code in there. It doesn't really matter what happens in there, as long as it doesn't modify I, okay? Because otherwise it changes the code. So as long as what is happening there doesn't touch I, maybe we're just counting a bunch of stuff, some global variables, I guess, because there's no parameters passed in, so whatever. But yeah, there's some code happening there, okay? So when we're looking at this code, and we're trying to analyze the time complexity of it, we need to say, how long does this code take to run? And would you agree with me with saying it's going to take however big n is, because that's the number of repetitions of the body of the loop that's going to run. So if n was equal to 10, then this code will take 10 times to run of whatever is in here. And yes, we could say that if this takes 1 second to run, then it's going to take 10 seconds to run, right? If n is equal to 100, how long is it going to take to run? Well, then it's going to be 100 seconds if each one takes 1 second, right? Let's say that it took 2 seconds to run the code in there, and then n was equal to 200. How long would that take to run in this system? Nobody's said anything? Maybe there's a delay. If the body of the loop takes 2 seconds, 400, there we go, yay! Maybe it was just a delay, because I saw a bunch of responses at the same time. So yeah, cool. Yes, 400 seconds. You guys are absolutely correct in that. Well done. So, when we're trying to analyze this, we are going to say that this code takes n time to run. It takes O of n time, okay? That is how long it takes to run. As you can see, the relationship between n and the time it takes to run is a linear relationship, right? The bigger the n, the bigger the time it takes to run, but it's linear, right? You know, you go from 100 to 200, it's going from 100 to 200. Even if it's multiplying it times 2, it's still a linear growth, okay? Let me put to you another version of the code. Let's say that inside of this loop, we have another loop, okay? We're gonna have to shrink it a little bit so it fits, but you get the idea, okay? And then here we have some code. Yeah, this is still safe to run, although it's kind of crazy to run this way because we're using the I twice, but we should be okay because scoping rules, right? Scoping rules means that that I is not gonna mess up the other I from above it. At least it shouldn't. But if you want to be paranoid about it, we can make them J's. So yeah, this will take quadratic time. You are correct, but why? Well, it turns out that if you were to type this in a computer and maybe write a global variable called C and then do C++ in here and then put n to be 10, you would find out this runs 100 times. So C would be equal to 100 after this is done. Use a static variable for that, actually. So you don't use globals. Use a static, yeah, use a static function in your variables to do that. So anyways, what this means is that because the loops are nested, it turns out that every time the inner loop runs through its whole course, which let's say n is equal to 10, so it runs 10 times, the outer loop will only run 1 time. And because it's also in relation to n, it means that it's going to be n times n, which, as you said, is indeed quadratic time. Okay? Let us put numbers in. Let's say that this n was an m. And n was equal to 5 and n was equal to 6. How long would this take to run? In each one, and this takes 1 second inside of here. The multiplication would be, and I won't wait because I'm going to go fast, but it would be 6 times 5 times 1, which would be 30 seconds, right? How would you represent this in terms of the big O? So you would put O, and instead of putting n squared or putting n, you would merely put n times m, okay? And I like to use a little dot for multiplication. I don't know why I picked that up at some point. So if you see the dot, it typically means multiplication. So that doesn't usually happen though. We usually only base it on one variable. But I wanted to make you aware of that. Some cases you will see asymptotic complexity in terms of multiple variables. A very, very common example of that is when you're dealing with strings. And sometimes a string algorithm is not just the speed of it is not just based on the number of strings, but also how big the string is. So the string length comes into play. Typically, that's the second variable. So when you're doing string matching, I have seen that be the case. So yes, there's a delay for sure. I know you guys are answering fast, so it's like a 10-second delay. But yeah, so that will be n squared. Okay, so I think you're starting to get the idea of how we're representing this in terms of n. Okay, we are looking at code and we are analyzing it in terms of the number of repetitions that it's doing, right? And it doesn't really matter the time this takes to run, because what you do is once you physically time it on a specific machine, you can just multiply that number times your n, and you're gonna get, you know, whatever the time it takes in that system, right? So there's a lot of other different asymptotic complexities, and I have them right here. So I'm just going to, can I even do that? It's not letting me. It's kind of glitching. I'm scared it's going to glitch out again. I want to copy and paste them, but it's not letting me. Okay, so I'm not gonna risk this thing breaking down again. So I'll just copy them by hand. But let me go ahead and put a couple of them. Actually, before I put them, let me put one more, because this one usually gets people. So let's say that we have for int I equals to 0, I is less than n. I times 2. Okay? What are you going to do with that one? Oh, well, that doesn't mean anything. That's going to loop. That one's infinity because it's going to loop forever. But I times equals 2. Okay? That means I equals I times 2. This one's also going to run forever. Damn it. Do you see why this one was going to run forever? It's because I is 0 and it's going to keep multiplying times 0. So here. Now it's not going to run forever. By the way, I did that exact same problem in one of the midterms in the past. And most people didn't catch it, and they all said like, "Oh, this is the answer," and it was right. At least what I was thinking in my head. Except for a couple of people that caught it, and I was like, "Oh, that's cool, you know. You guys like lawyered me on that and said it's gonna run forever." But hey, maybe they thought it was a trick question, and they were like, "Oh." So yeah. So how long do you think this is gonna take to run? Log time. You're thinking this is going to take to run log time. Why? What are logarithms even? See, now I'll put you on the spot, probably. No, so I won't. I guess I'll just. I won't put you on the spot. Otherwise, you'll stop contributing. But okay, let's kind of just look at this. Let's throw. This is one way. Whenever you don't know what is happening, you can just throw some numbers in, and then we can see how the numbers grow and see it there. Exponent. It takes to get a base to give given number. Right. Yeah, that's what logs are. And I do have a planned mini log lecture to go over. Probably next class. We'll see how long this part takes. But let us kind of just see how this grows. Okay. Let's start. Maybe not 10, but let's say n is equal to 20. Okay. You gotta be kidding me. I think it broke again. Why is it doing that? See, what happens is the pen works, but I can't write anymore. The laser pointer works. Oh, there we go. Fix itself. Maybe switching to the laser pointer fixes it. The laser pointer didn't used to work, by the way. Like that's literally the first time I've ever seen it work in presentation mode since I got the iPad. The whole last spring did not work and summer. So okay. Anyways, maybe that's a fix. Switch to laser pointer and switch back. See, it's debugging. All right. So, okay, I starts at 1, and then from there I becomes I times 2 is 2, so it becomes 2, and then 4, and then 8, and then 16, and so on. But if we set n is equal to 20, then it's going to go one more time to 32, and then it's going to stop because 32 is bigger than 20. Okay? 1, 2, 3, 4, 5, 6. So we got about 6 of these for 20. Okay, let's throw in maybe 2 more set of numbers to kind of get a better feel for it. So basically, anything over 100 is going to run 7, and then pretty much even 200 is going to just run 8 times. Okay, so we go analyze the relationship between these. And so it turns out that you are indeed correct. This is logarithmic time because it's going faster than linear time, right? Linear time would mean that if n was equal to 128, we would get 128 repetitions in the loop. This for sure, even with such a small number, you can see that it's going to do less than linear time. And it's not half of linear time, it's not a quarter of linear time, but you can see that it's sort of an exponential relationship. And as you said, logarithmic does mean in terms of a base of an exponent. And so you can see here that if this went higher, this went to 256, 512, and then 1024, you know, this would be like 9. If this was 500, you would do 9 here. If this was 1,000, you would do 10 here. If this was 1,009, you still do 10. And so you can see that even here, you know, this times this is, you know, even squared is small. So you can see that it's constantly growing. So that's kind of your sign that it's logarithmic, okay? And so there are other time complexities. And so let me show you all the ones that we have. And then after that, we're going to go back to this stuff then. Because I think then you kind of get a better idea, okay? So on the most basic case, we have the constant time. Some algorithms take constant time. What does that mean? That means that the size of the data is absolutely irrelevant to how long the algorithm takes to run. Okay? Now this might be like, huh? How is that even possible? Some algorithms are like that. An example of that is again the direct access map that I mentioned earlier on. So we will see that. Other example of that would be an algorithm that prints the size of a list if the list is stored already in an array, because you can just see the size of the array by looking at the index of the last item, right? So you can have constant time algorithms. They're not rare, but most of the time, except for direct access maps, they're not really useful, or at least kind of, I mean, everything is useful, but like they're not as amazing as they sound, basically. So left is the number of iterations, right is the number of n. Yes. This is the number of iterations on the left, and right is the number of n. As you can see, the number of iterations is way, way smaller than the size of n growing, okay? So, constant time. We all wish every algorithm was constant time. It would be cool if we could just feed in a billion numbers, snap our fingers like that, and now they're all sorted. That would be great, but it's not quite the case. Okay, from there, and examples of constant time, by the way, they don't always have to be like 1 second per se. Like I could have an algorithm that takes 1 second to run always, or 73 seconds. And also, you can also think of it in number of comparisons. So like I could have an algorithm that loops 73 times, regardless of the size of n. It just always loops 73 times. That will be an example of constant time still, okay? So constant time algorithms are not immediate. It just means that the time they take to run is irrelevant on the size of the input data that you're working with, okay? So it's important to make that comparison. There is technically algorithms that take 0 time in theory, but not in practice, because that would be impossible. Like something just finishes before it starts kind of thing. So, but you can see that in the books and stuff like that. From there, the next fastest thing are like the ones we're seeing above here, which are logarithmic time algorithms. There's also square root of n. Somebody proved in math that these are similar in terms of time complexity. I don't feel like doing the math for that, but you can do it. By the way, n you can rewrite as n divided by half, and then if you take the logarithm of both sides, then you do log 2 of n divided by 2. I do believe that that means that the 2 comes down here, and then this just becomes 1 like that. Yes. And so 2 log 2n is basically, this is just a number here. It's irrelevant. It's just times 2. So for all intents and purposes, they're the same. So that actually brings up something that I haven't talked about yet. As we go higher in these asymptotic complexities, you will find that such small things as numbers in front of them don't matter. Okay? So look at what I just did here. I said that there's a 2 here, and I said, it doesn't matter. For all intents and purposes, these things are the same as long as we're talking about base 2. You should probably be like, what the hell? You just got rid of a 2. Like, something that takes twice as long as something else is considerable, whether that's 10 seconds or 500 seconds. Well, I'm here to tell you that in the great scheme of things, it doesn't matter. In the great scheme of things, constant time, it matters, I guess, because it's constant time, so just the smallest. But even when you get to logarithmic, it doesn't matter a number ahead of a formula, okay? If we go even higher, you know, from this, the next one that you can see is something like, I guess, and this is what I have here. I don't remember which algorithm uses it, but I have one that says n log n. The most popular one is n log n. That's going to be your sorting one that I was talking very briefly about. From there, you can go to like n squared and all the powers, n to the 4th, n to the 5th, n to the 6th, and so on. Although sometimes you will see something like n squared log n, I guess. So maybe we'll put all these down here instead. At this point, it gets so big that a log n is irrelevant, just like a constant would be. But what I want to get to is, even within the n squared category, I am here to claim to you that if an algorithm takes 2n squared to run, and an algorithm takes 3n squared to run, square, not cube, I'm going to tell you that that's irrelevant. They're both the same. They're both going to be n squared. Why? Because these are constant values. And constant values are insignificant when you're talking about asymptotic complexity because of the small difference they make to something. You know, you might, again, this is a little bit counterintuitive because you might be thinking, well, one of them is faster because 3 is bigger than 2. And I would say that, yes, true. Technically speaking, the one on the left is going to be slightly faster. But when it comes to algorithm analysis, that difference is negligible and we don't care about it. We just drop that. So we drop the constants. And that's again going to come back to our definition up here. So maybe now is a good time to talk about the definition before we finish this. So let's talk about the definition of big O. Okay? So, I'm going to pull some notes here. So in computer science, big O notation is used to classify algorithms to how their running time or space requirement grows as input size grows. Okay? So, just to make sure that I made that point clear, this big O stuff works for both time and space, okay? We are just kind of really focusing on time today, but we can kind of talk about the space on Thursday, okay? Or Wednesday. We're going to get to the M, but yes, that M is the constant. That indeed, you probably looked at the definition already, but yes, the M is going to be that constant that we are talking about there, okay? So, what we want to try to understand and define with big O is as the size of our n grows, which is the size of the input or the data that we're working with, we want to see how that affects time or space, okay? That's the purpose of big O. We are trying to see how the size of the data affects time and space. And why is that important? Because again, we're analyzing if our algorithm is good or not, okay? And so that comes in here with the definition, okay? So we're going to say, let f, so the f here, okay? Let f be a real or complex valued function. Just don't worry about complex for now. Just think of it as a regular function. And g, a real valued function. So that's this function here. I guess, see, there's an expectation that you guys took calculus in this class. But let me make sure we're on the same page here, okay? If I write something that says f of n is equal to 2n, does everybody know what that means? Like what if I say f of 5, you know? this means plug 5 into n and multiply. So f of 5 would be equal to 10, right? Okay? I just want to make sure you're all, yes. I want to make sure you're all on the same page, because I mean, calculus is required, not necessarily because we use calculus, but because we do use some basic math, and we want to make sure that, you know, I don't want to lose you guys with the math, right? Because it might have been a while. So, okay, cool. Okay, so when we say g of n, we are talking about some function like that, okay? Just some math function that could be like g of n is equal to 2 times 8 times n plus n squared plus 55n plus like a bunch of other different variables, okay? That's all that we're saying, okay? Cool. So we're on the same page there, good. So g is a real valued function. That means that it's a function like we all see them, you know, y equals mx plus b, those kind of things. There's no complex numbers are like, you know, no, I don't even want to get there, but they're not like your regular math that you learn in high school, okay? So don't worry too much about that, okay? So they're both defined on some unbounded subset of real positive numbers. What that means is that we're strictly talking about positive functions, okay? There's no such thing as a negative function when we're talking about asymptotic complexity. That makes our life easier because we don't want to worry about negative numbers. I hope that's kind of obvious as to why there's no negatives, and that's because we can't write function that finishes before it starts, because that would mean we've invented time travel, right? You know, if we say that our function takes -5 constant time, it means that we can travel back in time, right? So that would be like, whoa. And then with space, that would be like opening some black hole or something. And so like, yeah. So that's not trivial too. So no worry about negative time, okay? So unbounded subset, what does that mean? Unbounded subset. Unbounded subset means that you can have as many numbers as you want, and they can be whatever you want, okay? So we are saying, like, think of it like sorting. You can have any numbers in your list, and those can be positive or negative, by the way. You can sort any number you want, and the list can be any size you want, okay? That's what we mean by unbounded subset. And subset of real positive numbers. Think set theory, which is Math 251. Set theory means that each set of numbers, like integers, is a set of all numbers. We're not sorting all numbers in like the universe. We're only sorting a subset of them. So that's why we're using the word subset, because our list that we're sorting contains real numbers, but those numbers are a subset, okay? We're not sorting all numbers in the universe, that kind of thing, okay? So that's what they mean when they say subset, okay? Such that g of x is strictly positive for all large enough values of x, okay? And you can find, if you want, I suppose I should reference you. I was gonna do it on the YouTube video, but let me reference you to that. Here, there's a little just Wikipedia. You can. So what I'm reading, that piece is the formal definition section of Wikipedia. So if you want to just copy and paste that, print it out, put it on your wall, at least during the test, then you can do that. So yes, okay. So going back to that, it's just a printed version of that, because when I teach, I'm normally teaching in front of class. So that brings us to our formula, okay? Now the formula, the way that it's written in Wikipedia is a little bit different than I have it here. So maybe I'll write it the way it's in Wikipedia first. So that is basically saying f of x is equal to O g of x as x goes to infinity, okay? The arrow means as it goes to infinity, okay? So all possible numbers that could go there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to infinity, okay? So what we're saying is that there's a function f of x that is equal to the asymptotic complexity in terms of big O of g of x as x goes to infinity, okay? That's the first part of the definition, okay? All right, second part of the definition. If and only if for all sufficiently large values of x, so we're looking at big numbers of x. Why do we care about big numbers? Kind of like that same reason as to the why down here I was showing you big numbers, because look at what happened with this logarithmic stuff. 6 to 20, that relationship could almost be like linear, like almost linear, not linear, but like quadratic. That could be quadratic for all intents and purposes. You only start to see that things are logarithmic or big if you go with the big numbers, because then you can really see how things separate. You know, you start out with just one item in your list. If n is equal to 1 here, then this is still just going to run one time. If that's your only like data point to look at, you could see that this is linear, right? So we need to look at the big picture with big numbers. So that is why in the definition, you see if and only if for all sufficiently large. The word sufficient is very risky to talk about in math because sufficient is like, it's like saying good enough. It's like, what is good enough? Good is a point of view, Anakin, that kind of thing. So really, that just means we need to look at big numbers to really analyze the big O of something, okay? So that's what it means, okay? So moving on. Let me know, I'm reading really slow, the definition, and trying to explain it, because, I mean, you can go home and read this while you're at home. You could go online and read this on your own, and then you're going to be lost. So I'm really just trying to walk you through that and explain it. So please, please, please ask questions if you get lost. I'm trying to just go over every single piece, okay? But we'll keep going, okay? So, if and only if, for all sufficiently large values of x, the absolute value of f of x is at most a positive constant multiple of g of x, okay? That's a lot to say. So what it's saying, the word absolute value here is kind of tricky, but because absolute value in mathematics means, again, hopefully this is refreshed, but ABS of -1 is the same thing as ABS of 1. All it means is take that number, and if it's negative, make it positive. If it's positive, don't touch it, okay? That's usually what absolute value means, okay? But really here, it's I don't know if necessarily that they're using that same sort of concept, but what it's really trying to say is that that the value that you're going to get out of the f of x function is going to be bigger than the g of x by some number. And that number is going to be a factor or something, a constant, okay? So like, if f of x gives me 5, and then, or here, if g of x gives me 5, and f of x gives me some number, that number is going to be bigger than g of x by some value, okay? So here, I am saying, I hope I'm not yelling. I'm kind of yelling, but I'm used to teaching in front of a classroom and, you know, want to be loud, but here I don't have to, so forgive me for that. I'm not yelling at you guys. So if g of x is equal to 10 whenever x is equal to 5, I'm sufficiently large, so maybe 500, and then f of x must be bigger than that, must be bigger than 10. You know, it could be 20 for all intents and purposes, okay? What we're saying is, as long as the x here is sufficiently large, so a really, really big number, then we still want f of x to be bigger. This is like, you know, imagine two companies competing, and somebody comes out with this, Intel and, or no, let's do NVIDIA and AMD. And NVIDIA comes out and says, I can do this amount of processing power, this amount of teraflops, okay? And then AMD comes out and says, nah, I can do that plus 1. So they're always competing, okay? Think of it this way. F of x always has to be bigger than g of x, no matter what. And then that number can be some constant, okay? So in this case, the constant will be 2, okay? So that's all it's really saying, okay? So, and it even says here, that is, f of x is equal to OG of x if and only if, so by the way, in math that is written as IFF, if and only if, there exists, in math, there exists, I believe is written as a backwards E, a positive real number m and the real number x sub 0 such that, and then they put the second part of the definition, which is f of x is less than or equal to m times g of x for all, that stands for all, x is less than x naught. So, don't panic. Okay, what this is saying is g of x is some function, and we're making another function of f x that always has to be better. We're like the AMD guys that we're always gonna have some, like we're gonna spy on NVIDIA and figure out what they're gonna make, and we're gonna make it slightly bigger, just because we can get the marketing for that. Okay, so what we're saying is we have to create this function f of x that will always be bigger than g of x, and if that is the case, then there must be some constant here, which can vary, by the way. It doesn't have to be always the same number. It can vary depending on the case. But it has to be there to make f of x bigger. Okay? For all, and this part means for all values. So like what is it saying is that if x is equal to 1, x is equal to 2, x is equal to 3, those equivalent values have to also match on f of x and still be bigger. So if I tell you G of like 120,000. I am guaranteeing you that f of 120,000 has to be a bigger number. If this is equal to like, I don't know, 9,000, then this has to, f of that has to be over 9,000, okay? How big the difference is between this is going to be some multiple of something. And that multiple of something is going to be your m. That's it. Does that make sense? Doesn't it have to be a smaller number for big? Oh, yes. Sorry. I might have flipped them. We're talking about big O, so sorry. Yes, I flipped. Yes, I flipped them. Sorry. Other way around. I was thinking omega. This is omega. This will work for omega. But for big O, you flip the less than and greater than sign, okay? So you will flip that, like that, okay? So in this case, this will be 9,000, and this will be 9,001, okay? Like that. Sorry. Flip that out. Okay? Why did I flip that? I thought I read it right. Oh, I know why. Because of the m here. Yes, that's because of the m. Yeah. That's why. We are saying that. So I was okay to say that. So this is 9,001 and this is 9,000. You threw me off. This is okay to say like this. But this thing holds true still because of the m. That's why. So f will have 9,001. G of x will have 9,000. But the m here is going to be bigger to make it okay. Now, what would this be okay? I don't know. Just put a 2. That makes it big. That makes it 18,000. That's bigger than 9,001. So, yeah. Yes. You're fine, though. You're fine. But, yeah. So really, we are saying we got the g of x and we got f of x. F of x is always going to be bigger. But if we put this little constant here, then we can still keep g of x bigger, okay? So what this all boils down to is that constants are irrelevant in the big scheme of things because of this m, okay? So when we're going back down here and saying that that square root of n and log n are the same thing, it's again because it's just a constant difference of 2. This is our m per se, okay? 2, all right? So I think from this it switches to the theta. Let's see. Many contexts are interested in growth of variable x to infinity. Yeah, the rest of that you can read on your own. We don't need to know that part. But okay, so going back to my version of the definition is this one. Okay, I think this version is a little bit maybe more, well, for me it's easier to understand, but it's the same thing I said in just a compressed method. So this is like the compressed version of the definition. Okay. So f of n is equal to O of g of n as n goes to infinity. So n is going to infinity when f of n is less than or equal to m times g of n for all n being greater than 0. Okay, so that's the compressed version of all the stuff that I went over. Okay, but it's the same thing. It's the exact same thing, just in a compressed manner. Okay. It turns out that for omega, all you got to do is flip the sign. You can see, I'll highlight it. So I am flipping, let's change colors. I don't like that yellow. This sign to this sign. Okay? That's the only difference between omega and big O. Again, big O is that upper bound. For omega, we're trying to find the lower bound, right? So we're trying to find something that is a function that is always going to be like smaller than the number. So if our number is 50, then our f of x should be like 49, right? And again, we can have an m, and in this case, the m can be, you know, a smaller number to keep it low, okay, or a fraction or whatever, okay? So, I even have here reminders for the for all and the infinity and beyond, I guess. So that is going to be the definition for big omega. It's just the same thing as big O, but you flip the sign, okay? Because instead of trying to get the top, we're trying to get the bottom. As the last thing, because class is about to end, and then we'll talk about big theta next time too, is let me show you a graph to better signify, okay? So suppose that I have my function f of let's say g of n, okay? Or here, let's just call this one different letters. Let's just say this is y of n, okay? This is my function that I have. What I'm saying is I want to create an upper bound function and a lower bound function. Well, that's kind of a crappy one. Maybe like this, okay? They don't have to be straight lines either, so yeah. The whole idea is to guarantee and say it's never my code is never going to be slower than that red line, and it's also never going to be faster than the purple line. It's going to be somewhere in between. And this is, of course, maybe experimental, but the point is that even if it's experimental, it's still always going to be bound by that. Mathematically, you are proving that your code can never be slower than the red line and never faster than the purple line. In between, it can go all over the place. And that theta kind of goes into that play. But that's kind of what we're saying, okay? So that's the picture version. Maybe it helps a little bit to understand. But like I said, this stuff is pretty tricky. We'll go over it next time. But that's all the time we have today. So like I said, don't freak out. This is probably the hardest topic of the course between this and recurrent relations. Do you mind briefly going back to the other definition that you wrote? Absolutely. This one or the one before it? The wiki one. Okay. Well, like I said, the wiki one is literally from Wikipedia, but which one was it? Maybe this one? Oh, 9001, okay. Oh, it's kind of messy, but you can always take a screenshot. Oh, yes, but all right. Like I said, you know, I tried in the past. Last time I did 302, I went straight to the math. This time around, I decided to try to do this code first, because I think this gives you a better idea of what this n is or this x is. So maybe this helped, maybe it didn't, who knows. I'll get you guys' feedback at some point on that once we finish the topic. So yeah. For assignment 0, you just need to sign and send the last page of the syllabus. Yes, that is correct. Why is it absolute value of f of x and not just f of x? That's just a math thing. In practice, you should never get a case of a negative. I think it's because, like, technically those lines could go into the negative area here, and then they don't want that to happen. You know, like this is technically bad right here. That's not good. So absolute value, I guess, prevents you from doing that by accident. For the graph, did you mean never slower than the purple line, never faster than the red line? If you're thinking about it in terms of space, then yes, because this could be time. And yes, this will be never slower than this line, never faster than this line, you know, in terms of time, okay? If we're thinking of it in terms of time that way. And this is size. Size of the data, or size of the input. Here, I'm gonna slowly move through this all so that the video captures it, and then you can just get the footage from the video. What might also help to show is my notes from last time around too. I don't know how to show those. I have them on the side. I'll show them next time. I'll figure it out. But yeah. Anything else? Other questions? Get the first, I don't know what the first assignment is due. So what you have to do, and I'll talk about it on Thursday, is I'll give another assignment out where I'll give you a bunch of code and you have to analyze the time complexities of it. So yeah. Shouldn't the faster and slower be flipped? Did I mess them up again? I might have. No. No, it's correct. It's correct because slow is high, fast is down per se. So yes. I mean, you can read the OG stuff. If you go to the Wikipedia, you can go and click on the sources of some of this stuff, and then read that. FYI, fun fact, I don't really say this, but Paul Bachmann, Edmund Landau, and Landau is pretty famous, I think, created the Bachmann-Landau notation, also known as the asymptotic notation, which is what we're doing. So you can probably read their work directly. But don't worry, analysis of algorithms will go into very detailed about all this stuff. See, there's a lot of it. Yeah, go to the Wikipedia. That has a lot of good information. Just go and follow that. But it is very important to understand it because when you're trying to publish something and say, this is a good algorithm, you have to list the asymptotic complexity of it. Otherwise, people will laugh at you and be like, yeah, sure. For the assignment 1, one of the comments asked for the creation of a class called system classes for unique create function system class as well, right? I posted on. I think somebody asked me that question at some point, and I tried to respond to it already. Basically, yes, you need to have a constructor for the class, and then that has to, you have to set the navigation of that, which means that you need to have an entity pointer. I call it navigator, and then you need to create a function that can set and read that entity pointer. So you need to have those. So basically, add the functions that you feel are required to get the functionality of the program working. So hopefully that answers your question. I'll hang in here for like 1 more minute if there's any questions. Yes, give it a try, and if not, send me a message, and I'll try to guide you further as well. Cool. Well, have a good rest of your Monday. It's early in the week, but hey, you only got 1 more 302 class, and then it's the weekend. So I'll see you guys on Wednesday. I shall have a good evening indeed. You guys as well, and stay safe. See you guys.